Trideep. Perfect. Okay. Maybe a couple of people. Just, I'll just wait for one more minute. Hmm? There are students. Okay. I thank everyone for joining for this week's Wednesday colloquium, and thank you for a bit of a turnout, although I expect more. So today is a special colloquium. I have Professor Gautam Mandal, who recently superannuated from the institute, and he is now associated with ICTS. I have, of course, a formal introduction planned by Professor Shiraz Minwala, but just to give one word from my side. So when I joined TIFR and not joined as a faculty, but as a VSRP fellow, Professor Gautam Mandal was our VSRP coordinator. You, of course, will not remember this. This is in 1999. And you welcomed everybody as a formally for that program. And so I still remember you from that very moment. So it has been fantastic. And thank you, Godamda, for many things in the institute. And of course, there will be other, places where we can again discuss that. But this is something I wanted to say, that this was the first formal introduction to you was through that ESRB program for me. So thank you. I have Professor Shiraz Minwala, who will formally introduce the scientific aspects associated with Professor Gautam Mandal, and maybe one story.
Okay. So, I mean, people sometimes say the speaker needs no introduction. In this case, it's, 100% literally true. Gautam, as all of you know, has been in TIFR perhaps longer than anyone else. Yeah. As you know, Gautam joined. Yeah. Okay. So the introductions often start with a PhD, but in this case, there is something special. Gautam, in his 10th standard school leaving exam, as you might know, stood first in all of West Bengal. Then, just to prove there was no coincidence, in his 12th standard school leaving exam, he stood first in all of Bengal. then there's a statue. then to prove that he was not deteriorating with age, he stood first in presidency college. Then he came to TIFR. Okay. Then he was a student at TIFR. Then was hired as a faculty member. While already as a faculty, he went for a 2-year postdoc at IAS in Princeton. You've not heard of that place, small place, but okay, okay, and okay, and then he came back here and has been here ever since. Gautam has worked on various aspects of quantum field theory, gravity, and string theory. There are so many things he's done. Well, actually, one continuing theme of his work the years has been what he's going to tell us about. The study of irreversibility in the arrow of time from 1983 onwards. Okay, but among the many things Gautam has done, I wanted to highlight one thing. Gautam, along with Spenta and Anirban, I think, found this a two-dimensional black hole solution in the theory of two-dimensional gravity, a theory that was well described by string theory, a solution that has intrigued string theorists and others continuously over the last 30 years. One thing that was really notable about that was that Gautam and friends were working on it, and so was Witten, and Gautam and friend did it 2 months before Witten. Okay. He's worked on several aspects of field theory, string theory, and gravity. Another thing that he worked on was on the study of, when it became clear that in string theory black holes were in the weakly coupled limit described by bound states of brains. Gautam and collaborators, spent Avinash and others, explained that that Hawking radiation from those black holes, not just the thermodynamical properties, but Hawking radiations of the radiation of the black holes, was also well described by this D-brane model, by two open strings colliding, producing closed strings, and he computed the spectrum of that and found that it was thermal and very similar to what you see in Hawking radiation. Okay, I won't say much more about his physics. He's going to tell us a lot about it. Stories. We had many stories, so I will be repeating myself. Okay. Okay. So a story. I mean, okay. I'm going to tell you a story that Gautam has told me, and that was actually came up in this reminiscence meeting. But I find it quite remarkable. Gautam, apart from being a great physicist, is greatly absent-minded. Okay, and so this is the story for when he went to visit someplace in Korea. Okay, he got out of his hotel, and knowing his nature, he thought he would look around and note the landmarks so he could make it back to his hotel. So he memorized a certain signboard, okay, which turned out to read something like Samsung. It may not exactly have been Samsung, but it's a kind of signboard that there were order 10 to the 4 of in Seoul. So when he dutifully got lost while going back home, he realized that what he'd memorized was not very useful. So after some circling around, he eventually made his way. I hope I'm not getting it wrong. He eventually made his way to a police station, and the police. There were some other details, but eventually the police agreed to drive him home. I mean, drive him to the hotel, thinking he would be less trouble that way. So they drove him to the hotel, and Gautam thanked them and got out and went to his hotel. But a minute later, the car came back with siren blaring because Gautam, on getting out of the police car, had taken the policeman's backpack and okay, so with no further ado, thank you.
Hello. Okay. Thank you all. Thank you, Jyotishman, and thank you, Shiraz, for this wonderful introduction. So I'm going to tell you about some aspects of the arrow of time. I'll explain what I mean. And together with that, I'll also tell you a bit of my own arrow of time in research, starting from 1983 onwards. So I'll try to compress in 1 hour various aspects of my research involving this arrow of time done over 42 years in 1 hour. So let's go. Is this a pointer? It doesn't work. Is there a kind of stick?
This is the top button that
Yeah, it doesn't work.
see this.
Oh, I see.
Yeah.
Okay, all right. Okay. So when I was a BSc student in college, I encountered this rather beautiful book by Nalika called The Structure of the Universe. It's an excellent book with remarkable insights. In particular, it has a priceless chapter on arrows of time. Okay, so that was the beginning. So it talked about 3 arrows, at least I think. Thermodynamic arrow of time, the one that says that a cup of hot tea gets cold and stays cold and never the other way around. The second, the black hole arrow of time, the one that says black holes can only absorb things but not emit. Cosmological arrow of time, the one that says our universe only expands in time. So I do not remember if the following is described also in the book, but there is also another interesting arrow, which is the arrow of life, the one that says that with time, more and more complex life forms evolve. So how does one maneuver this?
Maybe you can use the stick.
Yeah, I think stick is better. Stick is better. Okay. So the arrows, especially A and B, the first two, a priori seem to be in conflict with the basic laws of motion, which are time symmetric. And these are time asymmetric things, right? So for example, in the first one, the molecular collisions are time symmetric, yet the end result of the motion is time asymmetric. So here's a cartoon video of gas molecules in this room, let's say, which are colliding against each other and also against the wall. If you reverse the video, it looks pretty much the same. Okay, so it's time reversal symmetric. So by time symmetric, I always mean the time reversal symmetric. Okay, so you reverse the video, it looks the same. Still, thermalization seems to happen in the following way. So let us say that in this room, we take all the gas molecules and put them in one corner, leaving very few around like this, and let it evolve from this initial configuration through the same kind of things that we saw in the slide. At every moment, you could go back, reverse, things look the same. But if you watch after a while, you see that they have all spread out in the entire room. Now, if you reverse this, you will see something like this. That never happens. But microscopically, if you look at the thing with a high, very powerful zoom camera, it seems to be an allowed process. So we do not see the reverse happening. How come? So, so now I found, while I was fascinated by this arrow of time of thermodynamics, I didn't know about the black hole arrow of time. No, I just read, but I was fascinated by this arrow of time of the second law of thermodynamics. I found a paper in the American Journal of Physics, which claimed that the author has proved the second law of thermodynamics starting from Newton's laws. So that was absolutely fantastic to me. Wow. So then, however, on closer inspection, the paper turned out to be wrong. Okay. So that was my first entry. So I wrote a note, and that got published in the American Journal of Physics. And so that was in 1983. And so here it is. So the upshot is that you cannot have an exact derivation of the second law of thermodynamics from Newton's laws of mechanics, which are time reversal symmetric. If you find such a derivation, it is wrong. So this is like the Reserve Bank warning. You know, somebody promises something and don't believe. But on the other hand, the second law seems to be true. How come? We'll keep coming back to this question, but before that, let's visit the black hole arrow of time. How about the black hole arrow of time? First of all, what is it? So let me try this. Okay, so here's a binary star system. So this is the normal, this is a normal star, and its binary companion is a black hole. So some stuff has gone from the normal star to the black hole. So this is allowed. Okay. What's the reverse thing? The same stuff comes out of the black hole and goes to the normal star. Okay. This is not allowed, it's disallowed classically. Okay. Quantum mechanically, actually, as Hawking showed, that a faint radiation is allowed to come out of the black hole, but it's a Planckian emission. Okay, it's a thermal emission, and it's not the time reversed event of the object that fell in. Okay. Now contrast this with the time reversal symmetry of quantum mechanics. So here's a molecule here, and there's a photon. Okay, the photon can be absorbed by the molecule, and the reverse. So this is allowed, and the reverse is this: a molecule emits a photon, that is also allowed. This is allowed. Why is the situation different for a black hole? Okay, is the black hole not a standard quantum mechanical object? So the question that, yeah. Yes.
So it's not specifically to black hole as such, right?
No, but the black hole cannot emit. A neutron star can emit, in principle.
Yeah, but it will not happen it will not go back.
So the question is that why is the black hole different from a standard quantum mechanical object? That you can include a neutron star in that.
Okay. So it has nothing to do, your statement is that, of course, Hawking radiation is not there from a neutron star, I know. But your argument will be still, you can't have radiation coming
out of a black hole.
Okay. So
we can't have emission. Classically, we can't have emission coming out of a black hole. The time reverse process of the absorption, and whatever is emitted, that's actually not the time reversed phenomenon.
Okay, so it's nothing to do with accretion. That's what you're pointing. Yeah.
Oh no.
Yeah.
It's
Okay.
black hole. It's black hole. That binary system has to have a black hole in that.
Yeah. Okay.
Yeah.
Okay.
So can one describe black hole by standard rules of quantum mechanics? Is the black hole not a quantum mechanical object? So before that, one should ask: can one describe gravity by standard rules of quantum mechanics? Okay. So if you want to describe gravity by standard rules of quantum mechanics, you would like to apply the rules of quantum field theory to gravity, okay, which is described by this thing called the Einstein action, the Einstein-Hilbert action. And you would like to describe, let's say, graviton scattering by Feynman rules. So the leading order Feynman rules called tree diagram, they are all fine. So there are two of them like this for 4-point functions for graviton scattering, and they're all good. However, when you want to talk about quantum correction to graviton scattering, you need to include these loops where the energy of these things called the virtual particles, where the energy of the virtual particles is allowed to go all the way from 0 to infinity. Okay. And the problem with gravity as against electromagnetism is that the charges which sit here, okay, and are part of the loop integral, the charges are not independent of the energy. Okay, as you know, Newton's law of gravity is different from Coulomb's law. Okay, in Coulomb's law, you have Q1 Q2 by R square. In gravity, you have M1 M2 by R square. So the charge is the mass. Okay, and the mass is the same as energy. So therefore, the fact that the charges depend on energy, it leads to additional factors of energy which are also summed from 0 to infinity. Okay, so infinite charge factors come into this game, which are not there in electromagnetism. So it's there in gravity. So therefore, these diagrams turn out to be divergent. Okay, it's said in a somewhat simplistic way, but sort of approximately true. This seems to create a conflict between gravity and quantum mechanics because you can't describe quantum corrections by the standard method like this. Okay, so this situation is, this is rescued by string theory. So in string theory, the particles are replaced by these little loops like that, and these diagrams are, so instead of these diagrams, you have diagrams like that. That's the string scattering. Okay, and it was shown in 1974 that, okay, so that the leading order scattering, this is the leading order scattering. So in this diagram, if you take the point particle limit, in fact, you exactly reproduce to the dot, the same scattering amplitude that you get from Einstein theory. So therefore, the leading order string scattering reproduces the graviton scattering from. So therefore, it seems to be a step towards saying that string theory describes gravity quantum mechanically. How about quantum corrections at higher orders? Okay, so there was a problem here of divergences. That problem goes away in string theory because when you do this loop calculation in string theory, so the virtual strings, okay, so you want to take the particle limit of this, right? So in which the loops become infinitely, the point-like, but the virtual. So if you do take the point-like limit of this, you get some diagram like this one, which is divergent, okay, in which everything has become point-like. But in string theory, because of some internal, requirement of string theory, the virtual strings here, they cannot become infinitesimally small. Okay, there's a minimum length requirement of string theory. Okay, this is called the string length. It's something of the the same similar to Planck length. Okay, so therefore this thing remains finite. So if you did take the point-like limit, you would have gotten some divergent result. But because of the restriction that the strings have a minimum length, okay, this thing is finite. Therefore, quantum corrections to gravity can be described within string theory. Okay, so therefore, gravity can be described by quantum mechanics using string theory. So that this last slide was about weak gravity in flat space. Okay, does it work for curved spaces and black holes? Because eventually we want to know whether black holes can be described quantum mechanically. Okay, so it works for curved spaces, but only if the metric satisfies Einstein equation. This is something very strange about string theory. String theory says that strings can propagate in a background space-time only if the background space-time also satisfies some conditions. This is not how it works for electromagnetism. There is no condition on the background, electromagnetic field that the propagation of an electron demands that the background electromagnetic field has to be something. On the other hand, the propagation of a string demands that the background metric has to satisfy Einstein equation or some close cousin of the Einstein equations. Okay, so these were so when I was sort of growing up in TIFR, all these fantastic things were happening, and I also had a little contribution here, which said that consistent string wave functions can be constructed in a curved space only if the background metric satisfies the Einstein equation. Okay, and this is something like a Schrödinger equation, which would be valid if this is an error term in the Schrödinger equation. Okay, the error term disappears if this equation, this term is 0. Okay, so this is like the cousin of Einstein equation. This is the Einstein dilaton equation of Einstein dilaton gravity. Okay, so now we found that there are some consistency requirements from string theory. Okay, so the consistent solution of string theory include a black hole. So the answer to that we found was that yes, indeed. So the equations of consistency of two-dimensional string theory admit a unique solution, that's a black hole solution, unique one-parameter solution. So let me, so in two space-time dimensions, these are the equations of consistency written in terms of the metric and two scalar fields called the dilaton and the massless scalar field T. Okay, so these are the equations. So what we found was that there was a unique one-parameter solution, which are the two-dimensional black holes, one parameter being the mass of the black hole. There's something like Birkhoff's theorem about symmetric solutions of Schwarzschild, symmetric solutions of Einstein's equations 4D. So in this work, we considered leading order equations at low energies. Subsequently, Witten generalized this to higher orders. This subsequently is within 2 days. So Witten was doing that on the first floor of this Institute for Advanced Study building, D building, and we were doing this on the ground floor. So we were 2 days ahead of Witten. Okay, so the string theory has black hole solutions. So that's something that we proved. Can we say then that this black hole is a quantum mechanical object? So the crucial test of this idea is to see if the black hole entropy, which is given by the classical formula called the Bekenstein-Hawking entropy, area of the horizon divided by 4 times G Newton, can be explained by counting of microstates of the quantum mechanical object, because you see string theory describes gravity quantum mechanically. So there must be some quantum mechanical description, and then you count the number of quantum mechanical states that corresponds to this black hole, and whether this can be explained in terms of that counting, the microstate counting. Okay. So in 2D, that microscopic counting was not possible in any straightforward manner. So there's a lot of work that has gone into that in that, as Shiraz mentioned. But after 5 more years, so one needed to wait for 5 more years till 1996, when Strominger and Waffa found a different solution, a 5-dimensional black hole solution in string theory, which satisfied the amazing equation that the Bekenstein-Hawking entropy is the same as the Boltzmann entropy. Okay, namely the area divided by 4 times G Newton is the same as log of the number of states making up that black hole. Now, I don't have time here to explain this solution in great detail. It involves string theory in 10 dimensions, out of which 5 dimensions are compact and 5 dimensions are non-compact. And and it also involves extended objects called D-branes, which are wrapped variously in the non-compact dimensions. But it's a simplified picture is the following. This will suffice for us, that the classical description of the 5-dimensional black hole is that in the 5 non-compact dimensions, it's a spherically symmetric object with 3 different kinds of lines of force, okay, which correspond to 3 charges. Okay, it's like 3 electromagnetic charges, 3 kinds of electromagnetic charges. So Q1, Q5, and P. Q1 denotes the number of D1 branes, Q5 denotes the number of D5 branes, and P denotes something that is called the left moving momentum. That so these are just the 3 charges. And here is the microscopic description. The microscopic description is particularly simple. So these are obtained by looking at the low energy limit of the degrees of freedom of the D branes, of the bound state of D branes. Okay, so they correspond to 1-dimensional gas of bosons moving on a circle, and they're supersymmetric partners of the fermions. What can be simpler? Just 1-dimensional thermodynamics. Okay, of free particles. Okay, like that. And so they can move this way, or they can move this way. So I call these as left moving and these as right movings. And each quantum mechanical state is just given by the occupation numbers, the occupation numbers of the left moving bosons and the occupation numbers of the right moving bosons. Okay, and you can even construct explicitly the state like that. The simplest of these states is what is called a BPA state, in which the right movers, there are no right movers at all, and there are only left movers. So the specific choice of the occupation numbers, that defines the microstate of the theory. And a particular black hole is described by any one of these microstates which satisfies the sum rule. Okay, that little n times this is the momentum, And this is the occupation number of that momentum, sum over them, that should be given by the product of the three charges. Okay. Now this is an easy, so how many such sets of occupation numbers are there? This is an easy counting. Okay. This is just given by the Hardy-Ramanujan formula, and the log of the number of the states, which is the same as the log of the number of choices of occupation numbers, is given by 2 pi times square root of Q1 Q5 P divided by 6. Okay, and that turns out to be the same as the following calculation. You compute the area of the horizon of this classical black hole and divide by 4 times G Newton, you get exactly this number. Okay. So this was the work of Stavanger-Waffa, 1996. So clearly, therefore, we are describing here a black hole as a quantum mechanical object. Okay. So this conclusively proved that the black hole was a quantum mechanical object. So summary so far. So it appears a priori impossible to derive a time asymmetric law, second law of thermodynamics, from time symmetric laws of motion, even though the second law of thermodynamics seems to be rather robust. We see it. Okay, we see this thing happening every day. By a similar token, since absorption and emission by atoms and molecules are symmetric processes, if a black hole is a quantum mechanical object, the phenomenon of absorption by a black hole and no emission, absorption and no emission, more correctly a faint radiative emission, seems to violate quantum mechanics. Okay, because it's not time reversal symmetry. Okay. In string theory, we found that gravity has a quantum mechanical description. We found that string theory has black holes. We found that string theory has a quantum mechanical model of a black hole. So therefore, there is no respite. The black hole is a quantum mechanical object. Therefore, if the black hole has an arrow of time, you must explain it. Okay, so that's the issue. So hence, the black hole is a quantum mechanical object. We must therefore address the issue in two. This one, how does the black hole arrow come from the time symmetric laws of quantum mechanics? Okay, this is the issue. So to address this question, we went back to this black hole and we looked at this. Can this thing be taken off, that whatever that thing is? Sorry. Ah, you did it.
I don't know. No, I don't think I did it. ये custom line भी
Okay, if it is too complicated, then let's continue.
Is that
Okay, that's okay. That's okay. Good, good. Yeah, this is fine. This is fine. Thanks. Okay, so all right. Oh, okay.
That's not going on.
Okay, all right.
नहीं जा रहा है उतना ही रहेगा ठीक है चलो
Okay, it's fine. It's fine. So now we want to address this question. Okay, how does the black hole arrow of time emerge? And now that we have a black hole, a quantum mechanical model of a black hole, we can ask the same question as we did for this molecule and the photon. Okay, so what we do is to consider the process of a black hole absorbing a graviton and becoming an excited black hole, or the other way around. Okay, the excited black hole emitting a graviton. Okay, and we want to ask our question about the arrow of time. So here's some kind of detail. So there's a configuration of left and right moving bosons, and a graviton comes in, and what it does is to split into a left moving boson and the right moving boson of half the energy. Okay, and the reverse process is something in which a left moving boson and the right moving boson of energy is omega by 2. They meet and emit a graviton of energy omega. Okay, so these are the two processes. You can easily, by using this is the interaction Hamiltonian between the graviton and the bosons of this 1 plus 1 dimensional theory. You can compute the amplitude, and let me not go into great details. So the amplitude that the black hole absorbs a graviton is given by this, and the amplitude that the black hole state emits a graviton is also this. Okay, and that's not surprising. Why is that not surprising? Because this way around it is this matrix element, and this way around it is this matrix element. They are related to each other just by complex conjugation. Because why is that so? Because the interaction Hamiltonian is Hermitian. Okay, so that's the main point about time reversal symmetry. Okay, because it's Hermitian. There is a complex conjugation, of course. In this problem, both sides are actually real, so the complex conjugation does not matter. But if you take mod square to get to probability, anyway, they are also real. Okay, so the microscopic amplitude is the same for both the direct and the time reverse processes because the Hamiltonian is Hermitian. This is a consequence of microscopic time reversal symmetry. How does time asymmetry arise then? Okay, we saw that if we consider the process of emission from a black hole, it doesn't happen. But here we seem to say that it happens, it emits. So here, the calculation that we did in 1996 was to we introduced the following concept of an inclusive process. We said that if we do not care about the particular initial and final microstates of the black hole, then we don't look at the microstate to microstate matrix element. What we do is to take the probability, the amplitude square, and then sum over the final states and average over the initial states. Okay, we sum over the final states and average over the initial states. This is what we also do in the CERN accelerators, okay, in particle physics. So as a result, you can think of this as taking the amplitude square, summing over the final and initial states, and dividing by the initial number of microstates. Okay. The other way around, now the role of the initial and the final microstates have been flipped. Okay. So here you divide by the final number of microstates. But now you realize in any normal system, the entropy increases with energy. Therefore, the number of states here is less than the number of states here. Okay. There's more phase space available at higher energies. Okay. There's more entropy. And therefore, number of states omega I is less than the number of states omega f. Okay. Is that clear? At higher energies. So now you see that the de-excitation probability, the emission probability is, so this is what I'm calling excitation. In case of the black hole example, it's absorption, and this is emission. Okay. So the emission probability divided by the absorption probability is omega I divided by omega f, which is less than 1. Okay. So it's because of our not wanting to look at the particular microstates that an asymmetry, time reversal asymmetry has appeared. Okay. So let me give some, in simple terms, a quantum mechanical system has a higher probability to go from a low phase space volume to a higher phase space volume. This is something, this statement comes from that procedure that you sum over the final states and average over the initial states. That procedure gives rise to this this statement. Okay. So let me give you now. I'll do an experiment. Of course, I should do an experiment. Okay. So this is this is a famous coin shaking experiment which I have done. This is a tabletop experiment. You can do this. You start with 10 coins, okay, all tails, okay. Then you shake them in a box and throw them on the table. This is a tabletop experiment. That's what I said. Okay. So these are actual experimental data, by the way. I'm not fudging. And you plot them with respect to time, the number of times you toss. Okay. So you start with 0 number of heads, then you have 4 heads, then you have 7 heads, blah blah blah, etc., etc. It goes like that. Okay. You can do better. You can compute the probability of the number of heads. Okay. As you know from your interview questions, or maybe 11, 12 questions, or whatever it is, what is the probability of getting 5 tails and 5 heads? That's the maximum, right? Because 5 tails and 5 heads can happen like H, 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 T, 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 or H, H, T, T, H, H, T, T, etc., etc. Lots of different ways. Okay, so that's the probability of getting 5 tails and 5 heads. Okay, so let's plot the probability. Okay, so we start with this very low probability of getting all tails here, I mean no heads here, and so on. So it seems to stay up. Okay, is there some kind of an arrow of time that appears here? Okay, let's see. So this is something that also comes from my famous experiment. Okay, and now there's Boltzmann and Shannon. They said that there's something better that you can do. Is not P, but minus P log P. Okay, so that's the entropy. So let's do that. Minus P log P. So here I have taken 200 coin tosses. I cannot do this. I don't have that much patience. So this I did in a computer by using random number generators. Okay. So what you see here is that this quantity, the entropy, increases, and it has these occasional drops. Okay, but other than that, it more or less stays up like this. Okay, and for larger systems, which here translates to larger number of coins, the curve is closer to monotonic. These occasional drops get rarer and rarer. They happen much later. Okay, this in classical mechanics is called the Poincare recurrence. They get rarer and rarer. Okay, so therefore, an arrow of time emerges if the system is large and has a dynamics equivalent to. So now I'm generalizing this from the coin tossing to real systems. Okay, an arrow of time emerges if the system is large and has a dynamics equivalent to shaking of coins. Okay, in technical terms, this is called the ergodic property, typical of systems exhibiting quantum chaos. Okay, this is a bit technical, but I can explain if you come to me. The way to see the arrow of time is to note that such systems typically satisfy what is called the eigenstate thermalization hypothesis. This is the beautiful stuff which says that typical eigenstate of a certain energy is not distinguishable from another one of the same energy so far as the expectation values of observables are concerned. Okay, different eigenstates belonging to the same energy behave very similarly. Okay, so that's the thing. There's some mathematics that I have done here. Okay, so the it basically says that the matrix elements of an observable between eigenstates of this kind of the same energy, they're more or less diagonal, and the diagonal value is given by the microcanonical average. Okay, so any of the microstates can be replaced by the microcanonical ensemble. That's what the eigenstate thermalization hypothesis says. And using this quantity, you can easily derive that the expectation value of an observable in an arbitrary linear combination of quantum states, which is of course dynamical. So as time t goes to infinity, the expectation value in the time evolving state goes to the microcanonical average. Okay, so that's called thermalization, and this is also an example, of course, of the arrow of time. Not all systems have this. There are systems and states that may not thermalize, there's this famous quantum scar states or integral systems, which, however, can still, or integrable systems, okay, they also don't have this ergodic property. However, even they can show local thermalization. We'll come back to this later. A more robust property, okay, so the definition of local thermalization is that if you have a certain subregion of a, of a system, then the part of the state that is seen in that subregion, that's called the reduced density matrix. The reduced density matrix in an evolving state asymptotically approaches the reduced density matrix in a thermal state. Okay, this is technical, but I just wrote this for completeness. We'll come back to this equation later on. Okay, so this was a heavy slide. Okay, so it probably requires 10 slides to explain more, but the main message here is the following, that the coin tossing experiment that I described, okay, is not just a cartoon. It actually describes a system, okay, which has this mixing property or the ergodic property, or something that exhibits quantum chaos and so on. Okay, and for that, one has a mathematical way of describing the arrow of time. Okay, namely this. This is what is called thermalization. Okay, so now let me go back to the black hole with this little detour. So we'll do this calculation now. So we'll do this calculation for the black hole. So for the black hole, these would be like one-dimensional gas or states of one-dimensional gas or bosons. This is an excited state, de-excited state. This is the calculation that we will do for the black hole. And this is what we found. Okay, so this is some work that we did in 1996 using the Schrödinger-Vafa black hole model. So as I said, so first of all, we found that the total absorption probability is given by the area of the event horizon. Okay, it's like that. If you send in a whole bunch of gravitons like this radially inwards, okay, then the absorption cross section is just the area of the event horizon. It's an intuitive result. So which is actually true also. The total emission probability has this ratio thing, okay, omega I divided by omega F times absorption. Okay, you can compute this and you find that it's given by this emission probability is given by a Planckian formula. Okay, in the classical limit, when you have a large charge limit, all these charges, like I said, Q1, Q5, and P, when all of these are large, then this Planckian spectrum, it just shrinks like that, shrinks. And eventually in the classical limit, it goes to 0. So the emission probability goes to 0, okay? And the absorption probability is the area of the event horizon. But the big bonus is by not going to exactly the classical limit, but looking at the subleading behavior, namely is Planckian spectrum. So what we found was that the emission probability is given by black body radiation. Okay, so that was the big bonus. Hawking radiation, which is supposed to be in conflict with quantum mechanics, is derived here by a simple quantum mechanical calculation in a string theoretic model, maintaining unitarity and all other hallowed properties of quantum mechanics. Okay, so this is something that two groups did. This is our group, and this is Shumit Das and Somin Mathur. So we both arrived at this result that Hawking radiation can be described quantum mechanically, and there is no, okay, so now in saying this, I said that which is supposed to be in conflict with quantum mechanics. Why is Hawking radiation supposed to be in conflict with quantum mechanics? Okay, the reason is the following. So here's the picture of a collapsing star. A star collapses, becomes a black hole. The time goes up like this, and so the initially, it's a pure state of collapsing matter. Okay, it can be, any one of zillions of states with number of the types of particles could be different, and they can be in different states of motion, and blah blah, and eventually let us say that they have formed a black hole. So the black hole eventually remembers only the mass of this object. All these possible pure states, okay, which corresponded to the same mass, they become the same black hole, at least so far as the geometry outside is concerned. Okay, the geometry outside is Schwarzschild geometry, which is unique, and that sees only the total mass. Okay, so this is the first part of the information loss paradox. Okay, that many different initial states go to the same final state. Okay, so here's in equations, you have these 5 initial states. The 5, it's not 5; it's many initial states. When you consider collapsing, so these are pure states that describe the states of collapsing matter. When you consider collapsing to a black hole, they all go to the same state. Classically, at least this is what it seems. Now, put in quantum mechanics, Hawking would say that they actually become Hawking radiation. So it's not a pure state, okay, but it's a thermal state. So all these different initial states, they just go to thermal states. This is even worse. Okay, so first of all, this is already in conflict with quantum mechanics. Why? Because if you start with 5 states, unitary evolution will say that they go to 5 states, not 5 to 1. Okay, this is what Schrödinger equation tells you. This is worse because here all these different microstates go to a thermal state. Okay, so that's a pure state going to a mixed state. Okay, so this is really bad news for quantum mechanics if you believe Hawking. Okay, so here's a cartoon. So we start with a pure state at t equal to 0. At t equal to 100, let's say it's arbitrary units. So some thermal radiation has come out, and there's some stuff inside the black hole. And let us say, so there is this is incomplete evaporation. Okay, there is still some amount of the black hole left. Okay, and there is thermal radiation outside. So this thermal radiation, what we did in our 1996 paper was to basically say that the part of the state that is visible here, okay, is actually thermal radiation. Now, a part of a state, which is called the reduced density matrix, okay, that can be thermal even if the state is pure. Okay, so this is the reason why we found that when we did our calculation, we got thermal radiation. Okay. But, however, this is for incomplete evaporation. What about complete evaporation? So the black hole keeps radiating. So eventually it radiates away completely. Okay. Then there is nothing like the inside of the black hole left anymore. Okay. So you don't have this device of saying that, well, the reduced density matrix, when you integrate over your ignorance of inside the black hole, then what you get outside is the thermal radiation. There is no inside of the black hole anymore in that case. This is complete radiation. So there's a lot of this is the crux of the information loss paradox. There's a lot of in case of complete evaporation. So there's a lot of interesting stuff that is happening in this area using the SYK model and the 2-dimensional gravity models and so on. Beautiful stuff. Yeah. Yeah. That's the hypothesis. Indeed, that is correct. That is correct. There could be a remnant, but there's a lot of problem with the remnant hypothesis also. Okay, the universe might get filled with remnants and get bogged down with this humongous amount of remnant density. People have done all those calculations. It has implications for cosmology. Okay. So let's say, but in this, using this two-dimensional gravity models, using something called SYK model, blah, blah, etc., you can address these questions and you can have some insights. Okay. And last year, we wrote a paper in which we had a model of complete evaporation of black holes using these SYK models, where we had a description of a complete evaporation of a black hole using entirely quantum mechanics. Okay, this work is still in progress. Okay, this is for last year. Okay, going back to the incomplete evaporation that we did in 1996, at least in the context of partial evaporation, black hole radiation can be understood in terms of normal thermodynamics. The black hole can be treated like a black body. The arrow of time is the same as that from coin tosses, namely that it comes because of the tendency to go from low to high probability. And the reason for that I explained, because we are doing this summing over final states and averaging over initial states. That's what we did. Hence, the black hole arrow of time, therefore, is the same as the thermodynamic arrow of time. Even if you don't explain either, okay, here we found that the black hole arrow of time and the thermodynamic arrow of time seem to come from the same source, namely going from low to high probability. Okay. Following the black hole calculations to its logical end, Mandal arrived at a revolutionary idea in 1997, which said that gravity in d+1 dimensions is equal to quantum field theory in d dimensions. Okay. In our problem, this d+1 was 3 and d was 2. Okay, it was two-dimensional quantum field theory. That's the quantum field theory describing the bosons. And the gravity, this part I didn't quite explain. So this is given, this is called the, ADS3. So it's some three-dimensional geometry. More precisely, this is the statement: supergravity in d+1 dimensional asymptotically anti-de Sitter space-time. So this is some geometry, d+1 dimensional geometry that is equal to a specific conformal field theory in d dimensions in an appropriate limit. Okay. There's an even stronger statement of this, which is a superstring theory in d+1 dimensional asymptotically anti-de Sitter space-time, is the same as a specific conformal field theory in d dimensions. Okay. We'll come back to this appropriate limit business later on. Again, this appropriate limit is important. Okay, it is only because of that appropriate limit that we can have a derivation of this arrow of time. So, okay, so that's a lot of. I can never manage these arrows. Sorry. All right. So this is quite a handful. Let me give you some cartoons for this. So this is what the ADS-CFT correspondence of Mandal suggests, that if you have, so ADS space, anti-de Sitter space, is something that has a boundary. Okay. So you have empty ADS space here. If you do, then what you have here is the vacuum of the conformal field theory. So you have a conformal field theory, you have the vacuum of that. Okay, that's the first simple correspondence. If you put a black hole in anti-de Sitter space, then you get a thermal state of the conformal field theory. Okay, so that's the other part of the conjecture. Okay, now here Shiraz and collaborators had this beautiful idea that. So, sorry, I should say that in this case, what happens is that the area of the d+1 dimensional black hole, this black hole area of this black hole, is the entropy of the d-dimensional field theory. Okay. So now, Shiraz and collaborators in 2006, they had this beautiful idea that suppose you have a fluctuating black hole, but not fluctuating slowly enough so that small parts of the black hole horizon can still be thought of as more or less constant. Okay, so then the area of this part would be the entropy of this part. Okay, so this gave rise to the idea of the fluid gravity correspondence, which said that a black hole with a fluctuating horizon corresponds to hydrodynamics, okay, of the field theory at the boundary. Okay, and then by using Raychaudhuri equation, okay, one can prove that the area element, okay, in time can only increase. Okay, the area can only increase. The local area increases. It's a local called the local area increase theorem. How am I doing with time? I have 10 minutes. Okay. Yes. Okay. All right. Thank you. So now, so therefore, because of this correspondence, the fact that locally the area can only increase says that locally the entropy can also only increase. Therefore, this is a direct proof of the second law of thermodynamics using the area increase theorem. Okay. So therefore, now, okay. So the area law, I should explain a little bit. So the area law is actually related to the black hole arrow of time. Okay. In the following intuitive way, area is a monotonically increasing function of mass. If the mass increases, the size of the black hole increases, the area increases. Okay. So the area is a monotonically increasing function of mass. Since the black hole can only absorb mass, its mass can only increase. Therefore, the size can only increase. Therefore, the area can only increase in time. Okay. It cannot emit. Therefore, the size cannot decrease. Okay. So therefore, the black hole arrow of time is the same as the area increase, as the is related to the area increase theorem. Okay. Right. So therefore, we again affirm that the black hole arrow of time is the same as the arrow of time of the second law of thermodynamics. Okay. Now, isn't this a puzzle? Because the left-hand side, the black hole arrow of time, is exact. It's a theorem. Okay, you can prove this by using Raychaudhuri equation, as I said. Whereas the right-hand side refers to a standard quantum field theory, which has time reversal symmetry, namely arrow of time of the second law of thermodynamics. Okay. So, don't we have a correspondence between gravity and quantum field theory, which would say this? Therefore, the arrow of time of the second law of thermodynamics must also be exact. Therefore, what is going on? Because this side is supposed to be time reversal symmetric. Okay. This is not a puzzle because supergravity in d+1 dimensional asymptotically anti-de Sitter space is a specific conformal field theory in d dimensions in an appropriate limit, in some appropriate limit of largeness of something, large charges, large something, etc., etc. So as I'm going to say later on, I might not get time, is that symmetries can be broken in the limit of largeness. This is something that we are familiar with. Okay, that's called spontaneous symmetry breaking. So this is somewhat analogous to the spontaneous symmetry breaking, that the arrow of time happens in that appropriate limit. So if somebody like that gentleman of American Journal of Physics, he said that, well, I have derived it in a certain limit, he might be right. But he didn't use any limit. He had an exact derivation, therefore he was wrong. Okay. Now, so this appropriate limit is similar to the large number of coin tosses in which the arrow of time emerges from time symmetric dynamics. As I said, the drops of the entropies, they became rarer and rarer, and they got pushed forward in time further and further. Okay. Right. So far we have shown, okay, so this is all about gravity, etc., etc. So far we have shown that the arrow of time of the second law of thermodynamics can be derived from the arrow of time of black holes. But suppose you didn't have this gravity crutch. We have also given an intuitive introduction to how the thermodynamic arrow, blah, 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 okay, whatever. Can we do better? Can we actually derive thermalization in well-known field theories? Okay. So now this part, so the literature on this is huge. I'll give you two examples of from my own work, both on local thermalization after a quantum quench, both involving integrable systems. Okay. What's a quantum quench? A quantum quench means a rapid change in Hamiltonian governing a system. This is a great way of generating non-equilibrium states of quantum systems, both experimentally and theoretically. Okay. This is popular, very popular these days. Okay, and to study thermalization in such a system. Okay, example 1. This is a 1 plus 1 dimensional Fermi fluid. I'll go fast. So this is given by some analog, some analog of Navier-Stokes equation. This is described by where rho here is the density and v here is the fluid velocity. Okay, fluid density and fluid velocity. What is the long time dynamics of this system? For example, does an initial configuration of rho of v thermalize? The answer is shocking in the sense that shocks develop. Okay, so 5 minutes. Okay, all right. Yeah. So, and the equations break down. Okay, so the shock is when the gradient of the fluid density diverges, and you can see from here that if the gradient of the fluid velocity, fluid density diverge, then the equations will break down, and they do. So when shocks form, and I will explain why shocks form. It's a rather generic phenomenon that shocks form in such things. When shocks form, these equations fail. Therefore, we are unable to study the long-time dynamics using these equations. Okay. Now, the correct approach to this problem comes from a formalism of the 1990s, developed in the context of string theory. Using that formalism, one says that you should describe the system in terms of phase space density, not real space density or velocity, etc., etc. Phase space density. What's a phase space density? Phase space density is a simple concept which reflects Pauli exclusion principle. It assigns a value 1 to a phase space cell of size h bar if it is occupied, and 0 if it is unoccupied. Okay. So these are given by droplets. These are given by droplets. The black portion is something in which the phase space density is 1. All the states, all these h bar cells here, they are occupied. Outside, the unoccupied. So therefore, they are white. The phase space density is 0. So this is a droplet which could be the, and the droplets are always bounded. So in the ground state, the droplet is always bounded by the Fermi surface. So this could be a system in which this last surface, the bounding surface, is a Fermi surface, and this could be a deformation. Okay. The equation of motion of the phase space density is something very simple. Basically, this equation of motion says that each particle in the Fermi fluid evolves by its own Hamiltonian dynamics. Okay, that's what this equation means. So if you start with some droplet like this, then this is phase space, this is x, and this is p. As you can see, the fluid particles here are the fastest because they have the largest momentum. So then, after some time, this guy has gone here, but the lower fellows are slower, so they have not gone that much. So it tilts. Okay. So when the tilt is so much that a vertical crosses this droplet in 3 places instead of 1, okay, a shock has formed. You can show this. Okay, trust me. Okay. So, but when you describe this in terms of the phase space density, it's just a fold, smooth stuff. Okay. So what happens in terms of real space density is the following. So this is this black curve is a phase space density, and this red curve is a real space density. You can see that the real space density is kinky here. So you cannot describe this evolution by Navier-Stokes equation of the kind that I showed. Okay, but this one we went on, and this actually matched the the numerical evolution obtained by diagonalization of whatever, some numerical evolution. So there's something that we did in 2019. So now this is the way to overcome the shock. So once we overcome the shock, we can of course go on to t equal to infinity. And what happens is that, okay, so let me just go back. Oh, Jesus Christ. Oh, excuse me. Sorry. Ow. Yeah. After a while, what will happen is that this guy will touch this box, right? And let us say we are considering a periodic box. Okay, so these fermions are moving on a circle. Then it will go on like this, right? But if it's a periodic box, then this part should be drawn here. So a finger appears. Okay. So that's what happens. Lots of fingers appear. Filamentation happens. Okay. And eventually, asymptotically, there are lots and lots of fingers, lots of filaments. Okay. Although at every time, however large, okay, there are these filaments which tell you precisely what the pure state is. The filaments of the pure state. But look at it from a little far, coarse grain it, you will find that the phase space density goes from 1 here to 0 there, through 0.9, 0.8, etc., etc. It's a continuous thing from, and for you, I have generated this movie, okay, and you see filaments happening here. So these just ignore these black lines. I didn't know how to get rid of them. So so now if you keep carrying on, you will find that this filamentation keeps. This is actually this is actual dynamics, by the way. This is not a cartoon. So anyway, so understanding of how a pure state can eventually behave as a mixed state, we got that intuitive understanding. Mathematically, this is what the equation that we had earlier, that if you do some amount of coarse graining, then you find that the reduced density matrix goes to a thermal reduced density matrix. Prediction of thermalization exponents. So this arrow is the final story. But if you stop short of going to t equal to infinity, then you can find out the power law exponents. Okay. So we did something with two-dimensional, thermalization of two-dimensional Fermi fluid as well. That's work that is going on. And okay, this is a bit complicated. So here again, okay, so I don't have time to do this. So there is some, there is some exponential approach to thermalization by, again, using the same result. This is in a different system. This is called critical quench. And, again, you can chase the pure state by looking at, these terms. And what we're finding is something interesting, is that how to really have, pin down the particular pure state, which is very similar to a thermal state, but it's still distinguishable from the thermal state. So this is an important ingredient in resolving the information paradox. So this is what we are doing right now. Okay, never mind all this. Okay, conclusion. I'm on time. Thermodynamic arrow of time can be derived sometimes rigorously without conflicting with microscopic time reversibility in some appropriate limit, large number of particles, large system, large something. This is somewhat similar to spontaneous symmetry breaking in large systems. In some cases, thermodynamic arrow of time can be shown to be the same as, and in fact derived from, the black hole arrow of time, and vice versa. Gravity is equivalent to quantum field theory in some appropriate limit of largeness. The black hole arrow of time is rigorously valid in that limit, but only in that limit. In many examples, the evolving pure state, even after a long time, can be distinguished from the mixed state by carefully analyzing the asymptotic behavior. There are interesting systems which do not exhibit thermalization. It's an open question to see how their behavior can be understood from a gravity perspective.
Thank you very much. The colloquium is again open for more questions.
Yes.
Like, I just have a very basic question, but you mentioned that you started off by analyzing the 2D black holes, but then you said that you had to wait for like 5 years until Strominger and Waffa told the solution for the 5-dimensional one. Why, firstly, why 5? Like, what's the reason for why was that 5D easier instead of the 2D? And also, like, was it later on, like, I don't think you mentioned, but like, was that later on verified in all dimensions that, okay, black holes are quantum mechanically explained? Because that was only for 5D.
Because that was the first time, a black hole solution was found whose entropy was explained by this way. Other black hole solutions have also been found later on, but yeah, it has to do with the fact that it's simple. It's simple. That's why. Yeah. So yeah, I can explain to you why the 5-dimensional black hole is a simple thing. The other examples which came up later was little. I mean, a lot of stuff is happening, by the way, in showing this thing that the Bekenstein-Hawking entropy is the same as the Boltzmann entropy. A lot of stuff is happening, even in the 2D black hole, which I said was the microscopic understanding was a little complicated. A lot of stuff has happened, and some of that is still happening. In fact, 2D black hole has reappeared in the context of what is called a JT gravity, and a lot of stuff is happening there. Yeah. So yeah.
Nice talk, sir. So
Thanks.
your core argument which you explained was the idea that when you have higher number of states and higher energy states, the fall probability is more than the rise. Like one way probability is higher than the other.
Yeah.
Right.
The rise probability is more.
Rise probability is more than the fall probability.
Yeah.
But isn't it similar to the coin argument where, I mean, coin thing where if you sort of shake more than you have basically higher entropy states more likely. And in that case, haven't you just reproduced the coin system in a black hole scenario? So haven't you gone in a circle?
I'm gratified that you have, liked my experiment so much. It is true, indeed. The coin experiment is it basically captures, standard, quantum mechanical systems rather well, which have this specific properties like the eigenstate thermalization hypothesis of quantum chaos and so on, because there is some amount of randomness that I'm introducing in this shaking of the coins.
But the idea that if you have a lot of coins, then the likelihood of 50-50 is high, can be just explained by like just basic probability, right?
Yeah,
quantum mechanics for that.
Yeah, indeed, absolutely.
Yeah.
Absolutely.
So it's much more core than the quantum mechanical explanation sort of.
It's sort of similar. I mean, they are also in the context of a large number of coins, you will use factorials, okay, and you will use Stirling's formula and so on and so forth. Those are the more or less the formulas which also appear in the black hole counting problems. Yeah.
Okay.
Is it possible to connect all the definition of arrows of time? Specifically, I want to ask about the second law of thermodynamics and the complexity of the life. Can these two definitions?
No, I have no idea. I mean, I'm just fascinated by that arrow of time. It seems to be a little anti-thermodynamic though.
Yeah,
things are becoming more and more complex.
Yeah.
But ask Jyotishman. I have no idea about that one, but it exists. We don't all evolve into lower and lower life forms. I mean, I hope not. I mean, although there are elections that are
Okay. Yeah. If we want to completely satisfactorily resolve this Hawking information paradox, we'd want the answer to the following question: that let's say I have two very high energy gravitons, they collide, they make a black hole, then eventually there is some multi-graviton state. We want to be able to find what multi-graviton.
Yeah.
Do you have any ideas how we can?
Yeah, no, that of course is a very, very good question. I mean, this is something that particle physicists also tried in a way to see whether black holes could form at the LHC, and signatures of that kind of compound object intermediate state as against so Gobindo might know better. So I think Dimopoulos probably had some argument about the spherically symmetric fragments rather than collimated things if black holes formed in the middle. So I mean, if one could do that, yeah, of course. But it has to behave, intermediate configuration has to behave like a black hole. So that's tough. You really need to have probably lot of energy, and yeah, lot of energy or lot of particles. Lot of energy is probably better. Yeah. I completely agree. Yes. If one could solve that problem. Yeah.
If there are no further questions or more questions that can be discussed informally, let's go and walk together with Gautam da and have some tea and snacks. Thank you, Gautam da, for a very nice presentation.
Yes, sir.
You explained that weak radiation
Yeah.
from the right absorption cross section